Hello, this is section 4.1 for Calc AB, and we're going to be talking about antiderivatives and indefinite integration. So the first example is just starting off. So find a function, capital F, whose derivative is lowercase f of x. And so notice you're starting with the derivative and you're trying to work backwards to get the original function. So, and you already know, to do the derivative of a polynomial function, it will decrease a degree. So if you're trying to go backwards, that's the first thing you'll want to do is add a degree to your 4, it's making it 5 of course, and then if you notice you do the derivative, so pull the exponent down in front and then subtract 1, you get back what you started. Okay? So that is an antiderivative of this function, because if I do the derivative, I get f of x, lowercase f of x. All right, so the definition of an antiderivative, you'll note the notation. It's a little bit confusing, but that's the whole idea, is if you find the antiderivative, you get back the original function. Okay. Now, you might have had an issue up here. You might have thought about this. So when we did this antiderivative, you get x to the 5th. That definitely works. If you do the derivative, you get 5x to the 4th. No question. But what if there was a constant out here? When you do that derivative, it's 0, but that's not represented in our answer. So what we do is, since you could have had a constant, like plus 2, and when I do the derivative, I would get 5x to the 4th because the derivative of plus 2 would be 0. So what we do is we put a plus c here to fix that issue. So when you do an antiderivative, you'll have to make sure you put a plus c. Now, in your homework, I think the first chunk of problems, it says find an antiderivative. Well, that's what we did up here. We found an antiderivative, but that's just one answer. By putting that plus c, you're officially finding the antiderivative, and that would cover all your bases in case there had been a constant. Okay? All right, so here you go. Find the general solution of the differential equation. And we've talked about the differential equation. So when you go to do this problem, you've got your derivative is equal to 1/2. So whenever it's a number, that was the slope of a linear equation. So you know the antiderivative is going to be 1/2 x, but then to do the general solution, we'll put the plus c to be safe in case there was a number. Okay, so this is the notation for an indefinite integral. We're going to talk about a definite integral in a couple of sections. But for an indefinite integral, how we write this, and this is where that differential equation is going to come into play. Remember when we wrote the dy over dx, but moved the dx over to the other side? Well, that's what we're going to do with that dx here. So, to get the antiderivative, to work backwards, this is the notation we use, this integral notation, and then this is called the integrand. And then we write dx, and that's your variable of integration. So then, to solve this, this indicates you're going to do the antiderivative of this function here. And that turns into capital F of x. And then plus c is your constant of integration. Okay. Now, we will go, in the next couple of sections, we will go into in depth where this notation comes from and how does it work. So, that's, I promise we will do that in the future. Okay, and it'll make a little more sense. But that's the notation. If you see this, I know I'm about to do the antiderivative of this function here with respect to x. Okay? So this goes into, remember, here's your differential equation. Well, you haven't moved it over yet. So when you move the dx over, there's your differential equation. And if you do the integral of both sides, notice there's a 1 here. So 1, the antiderivative would be y. And then when you do this antiderivative, it becomes f of x. Now, this right here, you can write f prime of x, but you could also just write f of x. So don't get caught up on the, like, you have to have a specific way of writing what's in the integrand, because that's not true. Okay, but just realize you're doing the antiderivative of this function that's here. So integration undoes differentiation. So that's where that anti-differentiation word comes from. Okay, so here's some basic integration rules. So if you do, these are your derivative rules, just to refresh your memory, and then we're going to work backwards. So if you notice the derivative here becomes what's in the integrand. So if ever you have 0, we know that, well, the derivative came from c. So you're doing the antiderivative of 0, which should have been a constant, because you know the derivative of c is 0. So that's the cool thing. if you look at the answer and do the derivative, it should always give you the integrand here. Okay, so when you're doing the antiderivative of k, well, a number came from a linear function, so it must be the slope. So it's kx and then plus c. Now, if you have a scalar, you can move that scalar out in front. You can do the antiderivative of each term, so you can break it up into two separate integrals. Here's the big one. So that power rule we did earlier, so if ever it's x to the n, what you're going to do is you're going to add 1 to the exponent and divide by the new exponent. And that's what we did up here. So if you add 1 to this exponent, you'll get 4 plus 1 is 5. Then divide any constant out in front by the new exponent. 5 divided by 5 is 1. So that's the power rule. Then your little jingle, sine, cos, minus sine, minus cos, will help you with these. And then, of course, secant squared, antiderivative becomes tangent because the derivative of tangent is secant squared, and so forth. Right. And then e to the x, the antiderivative is e to the x. Now, these you'll have to make sure you, especially this one's a little bit weird. So, and then 1 over x, the antiderivative is natural log of the absolute value of x, and those absolute values are very important. There's no restriction on the domain except for 0. But when you go to do the antiderivative, now you have a restriction on the domain. So that's why we have to put those absolute values there. And that is really important to make sure you do that. Okay. So now we go into just finding antiderivatives. So you're going to try to use these little basic integration rules that you'll be very comfortable with after you do some practice. You have to practice these problems. Okay, so first thing, just like with derivatives, you've got to rewrite your radicals. So that's what I did first. And then you just go in and make sure you're talking to yourself as you're doing this. So you're going to add 1 to the exponent and then divide by the new exponent. Or when it's a fraction, you notice you flip and multiply because you're dividing by a fraction. But that's where this is coming from. And then don't forget the plus c. That's really important. Okay? And then here I put over here, you can check your answers. You couldn't do this with derivatives, but antiderivatives you can. So if you want to just do the derivative real fast, so pull the exponent down and then subtract 1 from your exponent, you get the same thing back. Okay, cool? All right, now, just like derivatives, you might want to make your life a little easier by, like on this one, distributing the x before you do the antiderivative. Okay, so that's what I did. I distributed the x. Now I'm just doing the antiderivative of each term. So add 1 to the exponent, divide by the new exponent. Same thing here. So that 3 is a scalar, so it just stays in front. I'm going to add 1 to the exponent, so you get 2, and divide by the new exponent. And plus c is your answer. Now notice, just like with limit notation, as soon as you find the limit, you would drop the limit notation. Well, just like with integrals, as soon as you do the antiderivative of this integrand here, that integral and the dx drop away. We don't write it anymore. Okay, so these are very similar. So just notice I rewrote the integrand to make it nicer before I did the antiderivative. And just use the power rule in both of those. Here I distributed that, I pulled the 2 out in front, making it 1/2. And then I distributed the x squared to both terms. So that way I can easily do the antiderivative. And watch out for that 1 over x. If you try to do the power rule with x to the negative 1, so if you try to do this power rule with the integral of x to the negative 1, you'll add 1 to the exponent, which gives you x to the 0, and when you go to divide by the new exponent, you end up dividing by 0, and that's where you'll catch yourself. You say, oh, something's not right, and hopefully that will spark the memory of, oh, that's the 1 over x, that's the natural log of the absolute value of x. Okay. All right, I'm trying to look and see if there's any these are pretty straightforward. So when you're doing your jingle, sine, cos, minus sine, minus cos, now it's what comes before is the antiderivative. So negative sine, sine, cos, minus sine. Cos came before, so cosine's the antiderivative, if that helps you. Now here, clean this up, distribute it, and then watch out, secant, tangent, you know that that's the derivative of secant, but you have to know your derivatives. So you might need to refresh on some of your derivative rules. Okay, and don't hesitate. Remember those trig identities you did in pre-calc? Here's where they're going to pay off. So rewrite this so that you can actually do the antiderivative. Okay, and then the reason you might say, Cogswell, why is this one here? That's really easy. Well, yeah, that minus 3, if your brain is in derivative mode, you're going to discard it and say 0. When you're doing the antiderivative, 3 becomes 3x. So just be careful. All right, so find the equation. So this is where you're given an ordered pair so that you can actually find the c value. So you do the antiderivative first, plus c. Then plug the ordered pair in so that you can solve for the c value and actually get the actual answer that goes through this point. Okay, same thing for this one. Now, we haven't done any antiderivatives in the denominator, so move that x squared up so that you can use the power rule, just like with derivatives. Okay. Now this one, you have to do it twice. So you're given the double derivative, so you have to do the antiderivative once, and then use this to get the c value. That's where I'm using the c1. Then we had to do the antiderivative again, and so forth. And you'll notice, you might say, Cogswell, you didn't use the integral notation, and that's okay. As long as you're labeling and very clear with your work, you should be fine. Okay. All right, then here's a little application problem. So determine its max height. So a baseball is thrown upward from ground level, velocity of 10 meters per second. So I started with acceleration because that's the only information you know. How on earth do you get maximum height? Well, it's fun to watch to see how this works out. So you have your acceleration. Now you can do the antiderivative to get your velocity. And there's where you can use your initial velocity to get that c value. So now you have your velocity equation. Okay. And then you know at a max height, the slope of the tangent line is 0. So set that equal to 0 to get the time, which is what we did here. And then you can do the antiderivative one more time to get your position function. And then we know it was shot up from the ground. So that's why our initial height is 0. And then plug your time into that to get the height. Isn't that cool? So being able to do the antiderivative is going to be a very useful tool. Okay. Now this one's a little more complicated. So let's see. Yeah, I think we have time to go through it. So a car traveling 45 miles per hour is brought to a stop at a constant deceleration 132 feet from where the brakes are applied. So notice you're in miles per hour and this is feet. So I went ahead and did our conversions real fast. So this isn't, you're not using gravity with this one. So I just did a of t equals negative a, did the antiderivative. That's a number. So the antiderivative is going to be negative at plus c. And then you go through, you have your initial velocity is 66. That's the conversion, getting it into feet per second. They did the antiderivative of that. Okay. And it said let s of 0 equal 0. So that's how that c became 0. So velocity is 0 at 132 feet. So I was able to take our velocity function, set it equal to 0, solved for t, plugged t into the position function, and set that equal to 132. So that's a little complicated. You'll have to think through that, and we'll definitely talk about this one in class. But that's how I was able to find the a value. And once I had the a value, then I was able to plug it into these other equations to get the equations. So that's a little fun one for you to think it through. And if it doesn't make sense, definitely come talk to me. So then, how far has the car moved when its speed has been reduced to 30 miles per hour? Now that you have all your functions, you are golden. You're good to go. Okay. All right, and then this last little lesson closer, find the general solution of the differential equation. So get your d theta over to the other side before you do the integral. And you'll always have, with an integral symbol, you'll always have a dr, or a d theta, or a dx. You need to know what you're doing the antiderivative with respect to, so that's really important. Okay, now that's just another example. Okay, please make sure you do your homework and email me if you have any questions. Thanks.